Okay, so now what we're going to do is partition the data, and let's do 60, 40, 0, and then the HPBN. HP stands for high performance, BN stands for Bayesian network. Okay, now we want naive Bayes. Okay, and can run. So now look at the results. And here we have the cumulative lift curve, and all right, so there is one thing I forgot to do, and that is, okay, so when you use transform node, it's not going to automatically reject the old time. So like departure time, okay, so now we have binned departure time, right? So now departure time should be, now we should not use departure time anymore, right? So that should be changed to no. The rest of it is okay. I forgot about that. So when you use transform, okay, as opposed to there are some other like you let me put it this way. When you use SAS code, okay, when you use the transform node and use one of the default transformations like standardized or logarithmic transformation and things like that, then the old variable is, it can be rejected, and the new transformed variable is what will be used from that point onwards. Okay. But when you use SAS code to do the transformation, then that process doesn't take place. So you will have both the old one and the new one. So you have to make sure that you don't use the one that was transformed. Okay. So the old one should be set to no, and then you run. So now you look at the results, and again, you can look at each of them individually, but I'm going to just go to make sure that the event is delayed. So remember last time we talked about how to make sure that the event of interest is properly selected. The default will be descending. Okay, you have to make it into ascending if you want the one that's smaller value to be the event of interest. Okay, and here is our classification table information. Okay, and your lift chart numbers. Okay, you know how to prepare lift chart. Okay, so these are the numbers for that. Okay, so now this doesn't give you the ROC curve, because remember we talked about ROC curve. ROC curve is what? 1 minus specificity in the x-axis and sensitivity on the y-axis for various cutoff points for propensity, like 0.5, 0.6, 0.7, and so on. And how would these two numbers change? That is ROC curve, and the best ROC curve would be one that's straight, from the origin, go straight up to 1, and then it's all the way 1 after that. So that would be the best ROC curve. Now, to generate ROC curve, you have to use model compare, and that is in assess. Okay, so model comparison. So if you doing in model comparison, it will compare these two models now, and you can have as many models that you want. It need not be the same type of node like base. So you can have HPBN, and then you can have KNN, and you can have something else, and all of that can be compared. And click results, and you see the ROC curves here. Okay, so the naive or baseline is the diagonal line like that, and the farther the ROC curve is from that baseline, okay, towards that corner, the better it is. Okay, so specificity is the probability of detecting negative, that is probability of true negative. That's specificity, probability of true negative. So 1 minus specificity is probability of false negative, and you want false negative probability to be 0, and sensitivity is probability of true positive, and you want that probability to be 1. For all cutoff points, if that is the case, then the curve will be like that. Okay. That is, it will go straight up and like that. But that's not the usual case. So let's now, I want this, we have done this before, but I want to repeat it. Okay, just as a review. Okay, so how do you prepare an ROC curve? Okay, so now of course when you do a compare node, that will generate your ROC curve. But what if you want to generate it on your own? Okay.